All right, everyone. Thanks for joining us today. I'm Chris Cunningham, and I have a graduate student with me here from NC State, Ishtiak Ahmed. We're going to kick off a presentation today on behalf of Stride called Pedestrian and Bicycle Accommodations at CFIs. Before we get started, just a little bit about Stride for those of you who don't know. Stride stands for Southeastern Transportation Research, Innovation, Development, Education Center. And we are a part of this consortium of 10 colleges and universities called the Stride Center. The Stride Center is the 2016 USDOT Region 4, or the Southeast University Transportation Center, with the University of Florida as the lead institution. And the mission of that center is to develop novel strategies for reducing congestion. So as a part of that, NC State University, one of the consortium members, led a project looking at pedestrian bicycle accommodations at CFIs. Ishtiak Ahmed is the graduate student that's here with me today. He'll be presenting towards the end. But I'd also like to acknowledge two other authors of the work. Nagy Raphael, some of you may have heard of him, is a distinguished faculty member in our civil engineering department here at NC State. And Shannon Warcall, who was formerly with ITRI and now with Kittleson and Associates, who has assisted on this project. So just a quick introduction, CFIs, or continuous flow intersections. This is one of several alternative intersection configurations that remove conflicts between typical movements at an intersection to increase efficiency and sometimes even, or oftentimes actually, getting safety benefits. The CFI typically is implemented for efficiency reasons, not for safety. And we'll talk about that a little bit more later. But it is one of several treatments out there that you can use in lieu of a grade separation. Pedestrian bicycle crossing facilities are common at CFIs because they are in urban areas, but they can be complex. And so that's one of the reasons that we did this work. And CFIs, from a geometry standpoint, they have quite a large footprint with additional signals compared to a standard intersection, but usually have a smaller footprint in comparison to the grade separated option that would basically be the next option if you went from a standard signal and not choose some type of alternative. So let's talk a little bit first about the reason for CFIs typically being the vehicle. So let's talk a little bit about the operation. Typically, the key motivation for the CFI is that it is cheaper than grade separation. Instead of spending, $2 to 4, 5, even $6 million plus dollars on a grade separation, acquiring right of way, moving lots of utilities, this option can give a lot of benefit over a fairly long period of time. So it is considered often. And typically it's all about improving vehicular mobility, especially between the heavy through and the left conflicts. So if you look in the large picture here on the bottom left, the whole idea is to separate conflicts. And so the left turn typically, if we use the west to south movement, left turn heading westbound, conflicts with the eastbound through at a standard intersection, but we can remove that conflict by putting an intersection just upstream on the east side and then put another signal. And if we do this at multiple approaches, multiple signals, and move those conflicts around to gain efficiencies such that these don't conflict anymore. So now the lefts can go when the throughs go. If you look here at the bottom, the lefts no longer conflict. And so now the lefts can go with the concurrent through without a conflict. And so we gain lots of efficiencies in that. So just to make sure everybody's with us here, I think most people probably know the CFI. I don't know if I'm gonna get that to work. Let me do it this way. Why does not work? It's okay. We'll move on. I think we've done enough explanation. One second. It's over here. That's the problem. All right. Sorry about that. So a little bit of background. Our Around 2010, the North Carolina Department of Transportation, which implements a lot of super streets, sometimes called restricted crossing U-turns. But one of the things they get a lot of pushback on, or two main things they get a pushback on, one being business owners in the area don't like being redirected and not having direct lefts, but also there's a lot of advocates for ped and bike who push against the implementation of a super street. And so a project was done, two projects were done, one on the business side and one on the ped and bike side, to look at the accommodations on super street and looking at options for accommodating those users. Around 2014, several alternative intersection and interchange, that's what AI stands for, guides were put out by Federal Highway Administration. The newest one was in 2019 on the quadrant intersection. So that, if it's not already out, you should see that soon. And then the diverging diamond interchange, which has got ongoing updates to update the geometrics and safety and signals pieces to those guides, was published in 2014. And then the median U-turn, that's the federal highway name. The common name leading up to that was the Michigan left, was put in place also. The restricted crossing U-turn, which we call the super street here in North Carolina. And then it's even gotten a new name in North Carolina. And then what we're looking at today, the CFI, or the diverging left turn, is what Federal Highway calls it. So if we look at the different types of alternative intersections that we're getting guidance on, the super street is one that NCDOT has kind of tackled on the ped and bike side. The quadrant, the median U-turn, those two have already been addressed with just basic ped and bike facilities. But the CFI is definitely a complex one that has really not been addressed. And so we basically wanted to create a project similar to the DOT one, specifically looking at the CFI. And then third, you should be aware, if you're not, that there is some guidance that if it hasn't been put on the web yet, it's coming. I have my copy as one of the team members, the NCHRP 0725 Guide for Pedestrian and Bicycle Safety at Alternative Intersections and Interchanges. And so basically each one of those federal highway guides that was created, they specifically created a project to look at the ped and bike design at those facilities to try and design them as safely as possible. And so we know there's lots of good design options being created out there. So today's focus is basically going to take the CFI pieces that are in NCHRP 0725 and look at the operations of those different facilities that are recommended in the NCHRP document. So the goal, compare operations. This is operations focused of various pedestrian bicycle facility options from NCHRP 0725 at the CFI to provide increased guidance in the early stages of project design with the objectives of identifying unique factors affecting pedestrian and bicycle accommodations at CFIs using microsimulation, and then comparing the performance of the different crossing facility types for both peds and bikes. So from NCHRP 0725, there's a few options that several practitioners have recommended over the last decade or so for CFIs. The three that really rose to the top in several of those focus groups were what we call the traditional crossing, the mid-block crossing, and the offset crossing. So the focus of today will be operations at those three facilities. So a little explanation, the traditional crossing, this is the one, if you go to Utah, you can see some of the earlier designs here. The traditional crossing, each of the pedestrian and bicycle facilities are single staged. One thing you should focus on here is that when we're talking today about the divergent left turn of the CFI movement, we're just going to look at this southeast quadrant. And so we're going to talk about this offset left here, this left over for the CFI, and how it conflicts with the west to east or east to west pedestrian or bicycle movement here. And so here we have single stage crossings on all approaches. It's not an efficient design, but the problem here is that the left turn conflicts with the side street crossing here on the south side. So the left turn movement entering has a conflict. And because this problem exists, if there's significant pedestrian demand here, then we get a lot of inefficiency in the CFI that we thought we were going to gain with the vehicular movements, because now we have to serve 4 possible phases. So just real quickly, I could show this in a lot of different variations. So this is the simplest version. let's talk about the mainline movements. If we have throughs going, then the concurrent peds can go in parallel. But, excuse me, then the throughs can still go with the left turns now because they no longer conflict, but now the peds can't go. So we have to run the peds separately first if the ped push button is pushed. And then we cross the barrier and go to the side street movements. And now the concurrent peds going north and south can go with the north and south through movements while the leftovers go. And then we have to turn the peds off. And I think I have that wrong. Yeah, the left turns will lead into the through. So that would be 4 possible phases. And so it's not super efficient if you have any significant pedestrian volume at all, regardless of how well the design works, walking through it as a pedestrian or a bicyclist. The second option is a mid-block crossing. It's similar to the traditional crossing. The only thing we do is we take the north-south pedestrian movements and we shift them down to where the leftovers are, up and downstream. Now, this is primarily done for safety. So if you imagine in the traditional crossing with the pedestrian crossing movement moved up close to the main intersection, we have lots of different movements to cross. It's confusing. It's a longer span of lanes to cross. And so this would really be more for a safety treatment. And so if you know you've got a heavy origin destination from one quadrant to the other or vice versa, then you can set these up with mid blocks to help facilitate the movements and get them away from the main intersection section. And it does remove a little bit of the conflicts also. So the mid block signals are placed at the existing displaced left turn as I described. And then signal timing of the mid block does not incur additional delay to the through vehicular movements. And you'll see this, I think right as I get towards the end of my portion of the presentation, when we calculate the cycle lengths literally are the exact same for the traditional and for the mid block. And so from an operations standpoint, from a timing standpoint, they're basically the same. It's really just a safety treatment. But we'll see what happens when we look at the times, or the stop delay and such, the different performance metrics in a second. And then the third one is an offset crossing. So basically, the left turn conflicts, if you look here in red, that existed where the crossing used to be, we now offset that ped crossing on the other side of the left turn. So now that conflict no longer exists. And so we remove this conflict. Now we don't have to hold that left while the peds cross. It can actually cross between the through and the left turn movement, and we get rid of those two exclusive, or those two ped phases that had to be called separately earlier. And so the rings accommodating pedestrian bicycles are now only 2 phases. So we get our efficiency back. We tighten up the intersection a little bit for the peds and bikes. Okay, and then all crossings are multi-stage. So if we see here, we cross in one stage going from west to east or east to west, depending on where you are in the crossing. So let's just assume we're coming from the southwest quadrant. We would cross southwest with the left turns crossing. The left turn would end. And then now this movement can go with the through. And so it happens nice and clean. Now, one of the things that we're looking at, we're going to compare these 3 different CFI designs, but we're also going to compare them to a standard intersection. So this looks a little messy here, but basically what we have here is a standard 4-leg intersection. It's a 6-lane facility in both directions with dual left turn lanes on all approaches. And so if you can just imagine that that each of those CFI options, we're gonna show at the end here how that compares to the standard intersection also. So just keep that in mind. Now the geometry, that's not always a 6-lane with a dual left turn lane. The geometry is selected by looking at the B over C for the different volume combinations that we have for the CFIs. And so we'll talk a little bit about how we did that in a second. So the alternative scenarios that we generated in our simulation models for the bicycle, we chose 2 different options. You can walk with the pedestrian on a shared lane facility, basically using the sidewalk configuration like a shared use path up to the sidewalk, or you could have an exclusive lane on the road. And so one or the other is the option as the bicyclists. The pedestrians will always walk in the sidewalk. We also modified, or we compared 2 different divergent left turns or CFIs. So we had a partial CFI where only the leftovers are on the major street, and then we had a full CFI where the leftovers are on all approaches. And then for the right turn control type, we had signalized movements, and vehicles always yield to the pedestrian or the bicycle. So just building a little bit here. Vehicle movements here are shown on each approach with the stop bars, and then I'm going to animate a little bit to show you exactly what we meant on that last slide. So shown in blue here, there are exclusive bicycle facilities that we included, and so those would be going with the vehicular traffic in the through lanes. And then in green, where the pedestrian facilities are from each quadrant, we have shared facilities for bicycles and shared facilities for the pedestrian that would be combined, just to make sure everybody understands. Okay, so a few parameters in simulation you should be aware of. So the volumes, the way we created the volumes is we used a tool called CapEx, which means it stands for Capacity Analysis and Planning Junctions. This was created by Federal Highway Administration a long time ago, but it's had several recent updates in the last 6 to 8 years, and even more recently with some of the ICE tools coming along to include various facilities. And so we basically created our vehicle volumes based on the V over C of 0.7 for the facility. The speed distributions were important for ped and bike. If we're going to look at things like travel time and things like that, we needed the speed distribution for pedestrians and bicycles. So we collected field data on 6 North Carolina intersections where these types of designs were in play. And then simulation, we basically ran each simulation for 1 hour, and we replicated that 25 times. Okay, from the signal timing, semi-actuated signal system was assumed with standard detectors for each model, and then the cycle length was minimized using linear programming, and then the V over C for each vehicular movement had to be less than 0.85. This was one of the constraints that we put on it from a signal timing standpoint. And then you'll note here on the, like I was saying earlier, for the partial CFI, which is the leftmost portion of the graph, the cycle lengths here were the same for the traditional mid-block because we're just moving the pedestrian down to the mid-block, but it really functions very similar to a traditional from a signal timing standpoint. And then the offset, because we shrunk the crossing distance on each of the approaches by moving the crossing point past the left turn, the cycle length was a little bit smaller in those cases for the full and partial CFI. And Ishtiak now will talk a little bit about the performance metrics and analysis.
Thank you very much, Chris. The remaining part of the presentation that I'll be presenting are about the simulation results. So thanks, Chris, for giving such a nice introduction on the CFI. So before I start with the performance measure, let me go back a few slides. For example, here where we have the quadrants. So the performance measure results are divided in 2 parts. One is the route level performances and aggregated for each of the crossing alternatives that we have from the 3 crossing types and other variations. So as you can see here, there are 4 quadrants here, and we can divide all the routes into 4 categories. One is like crossing the minor street in this figure, which is either from between southwest and southeast or the northwest and northeast quadrants. The other one is crossing the major street, which is like they have to cross a lot of lanes for pedestrians and also for bicycles as well, because we have a displaced left turn. The footprint of the intersection is larger than a standard intersection. So that route category is like the southwest and northwest between these 2 quadrants, or the northeast and the southeast quadrants. The remaining 2 category types are the 2 types of diagonals that we have. So usually we have 1 type of diagonal, which is either going between northwest and southeast or between southwest and northeast. But in a CFI, like a partial CFI like this, these 2 types of diagonals have 2 different configurations. The ones that are facing the displaced left turn intersections, which are, for example, at the corner of the northwest. Let me use a marker here. So here is the diagonal that face the displaced left turn intersection, and this one also here and this one. So I'm terming that as a diagonal with DLT, or the displaced left turns. And the other ones is the southwest and northeast diagonals, which these two diagonals don't face the displaced left turn intersections. So let me go back to the performance measure slide. So we selected 3 performance measures in terms of the pedestrians, bicycles, mobility, the travel time, stop delay, and number of stops. A lot of these performance measures are used in many guidebooks. So about the travel time and the stop delay, if we compare different routes or different alternative scenarios, in many cases, travel times and stop delay give the similar trends across different routes. If those routes, like the lengths and the configurations, are very similar, it's just like the stop delay becomes a function of the travel time. However, in some cases, for example, the midblock crossing, we can imagine that some travel times for some routes will be much shorter than the other routes. So that's why we keep the travel time as separate. But in this presentation, overall, on an aggregated level, we found that these 2 trends give like sort of similar values or similar trends. Not values, the trends are similar across different alternatives. So in this presentation, I'm just including the stop delay and the number of stops, which is the number of stops is very important for pedestrian and bicycles. So let me start with the route level analysis. So this is for partial CFI, and in these 2 bar charts, I'm showing the most common trend of stop delay. So if you look at the left-hand and the right-hand side figures in these 2 in this slide, they have sort of the same trend in terms of the traditional at the left-hand sidebar, mid-block in the middle, and the offset at the right-hand side. And I have color-coded these bars by different user types, like pedestrians, shared bicycles, and exclusive bicycles. So the black lines here on the top of each bar represents the standard deviation from the simulation runs in terms of the stop delay. So here we can see a common trend which for these 2 routes, and same trend was found for many other routes as well. So this one is for the signalized right turn movement scenario and the diagonal crossing with the displaced left turn. And the trend here across all 3 users is that the mid-block crossing generated the highest stop delay among these 3 crossing alternatives. On the other hand, the offset crossing generated either the lowest one or like sort of somewhat similar to the traditional crossing. And this trend of like mid-block crossing having the highest stop delay was observed in many other routes as well. So this was for the partial CFI. This slide shows the trend for the full CFI, where we can see that in a full CFI, you have 4 displaced left turns. So the efficiency of the offset crossing increases compared to the other crossing types like the traditional mid-block. Because if you recall the phasing sequences that Chris showed, the traditional and the mid-block crossing have the similar phasing sequence, and they have 4 phases. If you have a full CFI where you have all the left turns displaced, then the offset crossing can run in 2 phases only. So that's what the benefit of that. You can see it in terms of the stop delay for pedestrians and bicycles. As you can see, the offset crossing generated the lowest stop delay compared to the other 2 crossing alternatives. The mid-block crossing is still having the highest stop delay because on the major street. So this is the diagonal, which is a combination of the major and minor street crossing. And on the major street crossing, the mid-block crossing is 2-staged. So this slide shows the trend of number of stops for partial CFI. And this trend is completely different compared to the stop delay, because the number of stops now has become a function of the number of signals that you face and the number of times they have to stop. So the most common trend observed across different routes, here I'm showing 2, which is a major street crossing and the diagonal crossing with displaced left turn intersection, is that the offset crossing has the highest number of stops. And the reason is pretty clear, because if you recall the diagram for the offset crossing, where it's multi-stage, and although it doesn't have a conflict with the parallel going left turns, now it has to, for that offset setting, it's now the pedestrians and bicycles have to stop more than once to cross the minor or the major street, and as well as for the diagonals also. So consequently, the offset crossing has the highest number of stops. The mid-block and the traditional crossing, in some cases, they have similar number of stops depending on the route type. And for many routes, we have found that the traditional crossing has the lowest number of stops, just like this diagonal route is shown here. So, and that trend remains same for pedestrian, shared bicycle, and exclusive bicycle. So this is the trend of number of stops for full CFI, and as we can see, still the offset crossing has a very high number of stops, where the traditional crossing has the lowest number of stops. Of course, we can see some little variations in terms of number of stops here. The exclusive bicycles for mid-block crossing generated a higher number of stops, but that difference between the offset and the mid-block crossing is probably not statistically significant. And we will show which of these differences that we are seeing on an aggregated level are statistically significant or not. So as I said, depending on the route types, for some routes, this common trend may vary. So here I'm showing two plots, one for the stop delay on the left-hand side and on the right-hand side for number of stops. And this is the deviation from the common trends of stop delay and number of stops that I've just showed. So this is the minor street crossing in a full CFI with signalized right turn. And as you can see, unlike the other crossing types, the traditional crossing generated the highest stop delay, and which is very similar to the mid-block crossing, but still the traditional crossing is the highest one, which is unusual a little bit. And on the right-hand side, we have, in terms of number of stops, the mid-block crossing is the one that is performing worst. And the offset crossing is having like a sort of in between the traditional and mid-block crossing. So there are several reasons behind this deviation from common trends. One is like some routes have like multiple signals, but pedestrians and bicyclists can cross these routes at once. For example, if those signals are having progression opportunities, like the coordinated signals we see like for vehicles. So this is one of the reasons. And of course, the pedestrians bicycles speed is a big factor to like progress through multiple signals at once. So as I've just mentioned, like on a route level, it's important to look at the route level, because if we are focusing on a single route type to compare different alternatives, then an aggregated measure will be misleading. And that's what we have been showing here in this slide. So let's take a look now at the aggregated level results. So these graphs are showing the overall comparison of pedestrian stop delay at a partial CFI. In each of these pairs, I'm showing the aggregated level stop delay. So this on the left-hand side graph is showing the stop delay of mid-block and traditional. And the reason behind pairing these two is to show whether the differences are statistically significant or not. So the mean values of the mid-block and traditional stop delay, the difference of these mean values were found 18.9 seconds, where the mid-block has the highest one. So that's why it's the mid-block minus the traditional stop delay. And the star marks values represents that this difference was statistically significant. For these charts in these slides, all these differences between mid-block and traditional, in the middle we have the offset minus traditional, and on the right-hand side we have the offset minus mid-block. All these differences are statistically significant. And it's pretty clear that the offset crossing is having the lowest stop delay, while the mid-block crossing, if we compare the mid-block with traditional, the mid-block crossing is having the highest stop delay. And the difference was like, the highest difference was between, of course, the two extreme alternatives we have in terms of stop delay, 29.2 seconds. And that difference was statistically significant. So this is an aggregated measure, like 29.2 seconds for pedestrians to cross or to use the facility. So here the results that I'm showing is for pedestrians only. And just to mention that bicycles on the shared path also generated like a similar trend, just like as pedestrian. And the full CFI also generated a similar trend as the partial CFI. So if you like understood that chart, this one, the following ones are also easy to understand. And this is showing the difference in trend between this number of stops at a partial CFI. So as I mentioned on the route level analysis and those results, the common trends are also reflected here in the aggregated level, where we can see that the offset crossing generated the highest number of stops compared to among the all three crossing alternatives we have. And this difference is significant, statistically significant, like 0.62 number of stops per user or per pedestrian here. And the traditional crossing, of course, as we saw in the common trend of route level analysis, it generated the lowest number of stops, which is also statistically significant compared to the mid-block and the offset crossing.
So it's interesting, I'll add one thing here, if you go to the previous slide, that the offset has a lower delay, but it's got a higher number of stops, so there's a trade-off.
Right. Yeah. So these results are about pedestrian, and as I said, the bicycles on the shared path generated the same results, or like at least the similar trends. The values were different, but the trends were similar. So let's take a look at the results for the exclusive bicycle stop delay. And we are seeing like a sort of somewhat different trend here. For example, the mid-block and the traditional crossing on the left-hand side is like it's flipped compared to the pedestrians stop delay, because now the traditional crossing has the highest stop delay. However, this difference between these two, which was generated by running the simulation models 25 times each with 1 hour duration, is not statistically significant anymore. So we cannot draw any conclusion that these two performance measures are different, or because they have sort of the similar phasing and other things are, the minor street crossing is particularly very similar between these two alternatives. So we are not seeing a statistically significant difference in terms of the stop delay. However, the offset crossing, that trend is still the same for exclusive bicycle. As we can see that it generated the lowest stop delay for exclusive bicycle as well. So this is a trend for number of stops, and same thing, like the mid-block crossing and the traditional crossings difference is not statistically significant. On the other hand, the offset crossing generated the highest number of stops for exclusive bicycles as well. So from these charts, there are several things which are pretty obvious from our simulation run, which is offset crossing, as Chris said. Like there are two things: the stop delay is generating the lowest stop delay for both pedestrians and bicycles, and it's generating the highest number of stops for all types of users. The traditional crossing is sort of like in between in terms of stop delay between the mid-block and the offset crossing, but in terms of number of stops, it's the best option among these three. So let's talk a little bit about our findings in terms of the comparison with the standard intersection crossing. So the standard intersection generated higher stop delay than the equivalent traditional or offset CFI crossing. And the main reason is that the number of phases and the cycle lengths are like, we have, although it's traditional crossing, like we still have 4 phases, but because of the displaced reference, it has still a slightly higher efficiency than a standard crossing. The offset crossing, of course, it either has like 3 phases in the partial CFI or 2 phases in the full CFI. So the efficiency is a lot higher. The cycle length is reduced, like less compared to the standard intersection. So that's why the standard intersection generated a higher stop delay across all 3 user types compared to the traditional or offset CFI crossing. On the other hand, if we look at the number of stops, the standard crossing actually didn't perform that bad, and it has a lower number of stops than the equivalent offset and mid-block crossing. And if you recall the offset and mid-block crossing setting, many of those routes have multiple signals to phase. So on the other hand, the standard crossings, every route is like single staged. So that's why we are seeing a lower number of stops in standard crossing. So these are important observations because when we are switching from a standard intersection to any type of CFI, and we want to put emphasis on one of the two or the three performance measures that I'm showing, these observations are important. And another thing important to note is that the number of stops, the experience faced by pedestrians and bicyclists could be different. I mean, the bicycles, if they have to face higher number of stops, they have to probably dismount and mount again. And so a lot of things we need to consider on a user level, which is like very difficult to quantify, like user level of comfort and these kind of things. So to summarize the major findings here, overall, the cycle length, number of crossing stages, and the progression through these stages are the major key factors that we have found from our simulation runs for pedestrian bicycle accommodations at CFI. For the shared use path, like the pedestrians and bicycles on the shared use path, in terms of stop delay, the offset crossing perform best because it's generated the lowest stop delay. In terms of number of stops, the traditional crossing perform best for pedestrians and bicycles on the sidewalks, because bicycles on the exclusive bicycles, what we have found that the traditional and the midblock crossing have somewhat similar trends. So for the exclusive bicycles, they experience the least stop delay and number of stops than bicycles on sidewalks. So if there is space on the site to put the exclusive bicycle lanes, it's always preferred to put that so that they have the least stop delay as they are moving with the vehicular movement. Regarding the standard intersection comparison, the traditional crossing in a CFI perform better than the standard intersection. But again, all these trends may vary significantly at the route level, depending on the type of the route. Yeah. So, Chris, do you have anything to add?
No, I don't think so. Sorry. We have some time for questions, and I have one. If you just use the chat box for that, that would be helpful. And we see these compared by total travel time through the various intersections for cyclists and pedestrians. It would be useful to know the total delay, including out-of-way travel, rather than, can you turn that off for me, Ishtiak? Rather than just stop delay, since the mid-block in particular looks like it could create significant increases in travel time compared to transverse. So Dwayne, the reason we didn't show, and correct me if I'm wrong, Ishtiak, but the reason we did not bother showing the travel time results is because, sorry, we're having a phone call coming in. Give me 1 second. Just hit the bird. It's because the stop delay, the travel time delay is basically the sum of the stop delay from the traffic control devices, any geometric delay that might be involved. It's basically a sum of all the different delays. But the primary measure of delay that travel time was capturing was stop delay. And so we basically chose just to reduce the amount of confusion in looking at the graphs to just show the stop delay. The results basically are the exact same. They have the exact same trend. Did we do any field studies to validate the simulations? We did not. And so this field studies for the STRIDE projects, the way the UTCs work, for those that might not know, the consortium has 10 members and the money is divvied out through the consortium to the various partners. And then inside each one of those university partners, there's usually around 3 or 4 projects that are being worked on across consortium members. So basically what I'm saying is there was not enough funding to really travel around and do validation of these various studies. Now, one thing we did do in 0725 is we went out to some of the facilities to get the actual design configurations and to actually capture some of the data from those facilities using focus groups and things like that to figure out which ones from a user experience made the most sense. So One thing that is interesting to us still on this project is how we can look at the operational pieces and overlay those with some of the user experience findings to see, what makes the most sense.